Okay, hello everyone. My name is Dr. Chris Satow. I'm a lecturer in physical geography at Royal Holloway, University of London. I'm a researcher who looks at past climates and their relationship with natural hazards. And that's the topic that we're going to be investigating today in this lecture. So we're going to have a look at volcanic systems, earthquakes, and tsunamis. And see how they are going to develop and change within the changing climate that we're experiencing and will continue to experience into the future. Climate change is obviously going to have a very profound effect on many of our natural hazards. So the obvious ones are the climatic hazards like heat waves and flooding, perhaps even storm systems like hurricanes. But what's less obvious is that climate change may also impact hazards of the solid Earth, so earthquakes, volcanic systems, and subsidiary hazards that come from those, like tsunamis. So the aim of today's lecture is essentially to look at those hazards and ask quite a simple question, really. How can climate change possibly influence natural hazards of the solid Earth? It's not an immediately obvious connection between the two. So just as an outline of what we're going to cover, we're going to have a look at volcanic systems, earthquakes and tsunamis. And in each case, as we go through this session, we'll examine how the climate and climate change has in the past and may in the future affect those natural hazards. There's also an activity related to this lecture which you can undertake as well in your own time. So there's two books that I would recommend for any of you who are interested in following up on this topic. The first is a textbook. It's really aimed at first year undergraduates, I would say, but probably A-level students could manage with this as well. It's edited at least by two researchers called Bill Maguire and Mark Maslin. It's called Climate Forcing of Geological Hazards. So this is an academic textbook, but Bill Maguire has also produced a sort of popular science book called Waking the Giant, which is, if you like, an easier read, but it's a great introduction to this topic of how a changing climate can trigger earthquakes, tsunamis, and volcanic systems. So we're going to start by having a look at volcanic systems, and before we get on to examining how the climate might impact those volcanic systems, I'm just going to run through a quick reminder of how volcanic systems are formed in the first place. So there's really just two conditions that we need to get a volcano. First of all, we need some magma, so we need some melted rock. And second of all, we need a way to get that melted rock to the surface. So we need some fractures in the crust to get this molten rock up to the surface here. Now, there's a few different ways that we can melt rocks to produce magma. The first is perhaps the most obvious. You can heat a solid rock, or the asthenosphere as we call it down here. It's just this kind of semi-plastic layer of the Earth's crust. We can melt it by heating it. So we might have a particularly warm part of the mantle which is creating heat here and melting the rocks to form magma, and that gives us the potential to create a volcanic system. The second way that we can melt rock is by decompression. So this is a little bit less obvious perhaps, but if you have a lot of pressure on a rock, it keeps it in a solid state. If you release the pressure, then if you release it enough, then you can melt the rock. So this is a nice block diagram which takes you through that process, which we usually associate with divergent plate boundaries. So where two plates are moving apart from one another. And the best example of that perhaps is in the mid-Atlantic. So under the Atlantic Ocean, we've got these two oceanic plates pulling apart from one another. And that process not only thins the crust, but it also decompresses the asthenosphere underneath. So this creates melt. And as we know, one of those conditions for a volcanic system is we need magma. So this pulling apart of the plates not only creates a gap for that magma to get to the surface, but it also creates a low pressure zone in the asthenosphere here, and that can create melting and provide a magmatic source. Now the third way that we can create magma is by adding water to solid rock. And this is the case at a subduction zone, which is probably familiar to most of you viewing this presentation. So this is a plate boundary where we've got oceanic crust descending underneath continental crust here. And the oceanic crust here carries quite a lot of water, and quite a lot of that comes actually from the sediments themselves, which are obviously deposited within the ocean. So that water is carried down to depth and heats up and enters the continental crust. And if you add water to the continental crust, you can melt it. So that provides another potential source of magma. And then if we have some fractures in the crust, we can get that magma out to the top and create a volcanic system. So in terms of the geographical distribution of these different types of volcanic system, that's shown on this map here. So melting by heating, that's a nice example of that is the Hawaiian Islands in the middle of the Pacific Plate, just here. In terms of decompression, I already mentioned, this is the mid-Atlantic ridge system here between the Americas and Europe and Africa. And in terms of melting by adding water, that's our subduction zone systems. That forms the very famous Ring of Fire, which goes around the edge of the Pacific with all our highly explosive subduction zone volcanic systems. So once we've got a magma source, once we've got some melted rock, the second condition we need to get a volcanic system is to get that magma to the surface. And we need some fractures in the crust in order to be able to do that. Otherwise, the magma is just going to sit there in the crust and not really go anywhere. It's not going to give us any volcanic activity. So there are essentially two ways that you can create those fractures in the crust and subsequently get a volcanic eruption. The first is perhaps the most obvious and the situation that we think about most frequently when we think about volcanic systems. If we get some injections of magma from depth here into a shallow magma reservoir or magma chamber, as we sometimes call them here, this increases the pressure within this magma chamber here, something which we call overpressure. And once the overpressure becomes greater than the strength of the rocks, those rocks will fracture, and we can create fractures above the magma chamber through this increased stress that's on the magma chamber, and the magma will make its way to the surface and erupt. That's the first way that we can create a volcanic eruption, and it's the one that was most familiar to most of us. The second way that we can create fractures in the crust and get that magma up to the surface to erupt is perhaps less intuitive and less well known. But it connects to our idea that the climate can be the thing which can drive volcanic eruptions. So I'll just take you through this diagram that we've got here quite slowly. So this is the same diagram as we have before. We've got this magma chamber here. We've got a reservoir underneath at a depth. But this time, on top of our landscape, we've got some glaciers. So I've tried to crudely put these glaciers in as big blocks of ice here. Now those glaciers, or indeed a wider ice sheet, are imposing quite a heavy load, quite a large mass onto our landscape and onto the rocks underneath. That's represented by these large arrows here. And actually that load is sufficient enough to keep the rock underneath from fracturing. If, of course, we have a situation of climatic change, perhaps like the one that the Earth experienced 21,000 years ago, where there's a lot of ice around at the poles. This is the last glacial maximum, and there's a huge load imposed upon this land surface. Then we can't form any fractures above the magma chamber to direct the magma to the surface. So we don't get many volcanic eruptions in this situation. If we warm the climate and those ice sheets or glaciers melt away, then actually that's a huge load that's taken off the crust. Think of these ice sheets maybe a few kilometers thick. It's a lot of ice that's pushing down on the surface of the crust. And so the pressure that's exerted on the crust reduces quite significantly. And that's enough to change the stress field in the crust to become out of equilibrium and become tensional. So there's an effect of pulling apart around this magma chamber here. And as you know, with most materials, if you pull them apart hard enough, you can form fractures. So that might be enough to direct magma, allow magma to get from our deep reservoir to the shallow reservoir, and then from the magma chamber right up to the top and erupt. So this is a really neat example of how climate change, in theory, can affect volcanic systems. So if we remove mass from the crust, if we remove, say, a large ice sheet or a glacier from the surface of the crust, the stress regime in the crust changes, we can form fractures, and through those fractures the magma can escape to the surface and create eruptions. And this is an effect which is gathering quite a bit of evidence now. So we're able to look back through records of past climate change and understand how the number of eruptions that occurs at different times changes as we go from conditions such as that we've got on the left block diagram here, where we've got this large ice sheet covering a volcanic topography, and the magma is inhibited from getting to the surface. As we change and go through to a deglacial state, so something like we have today, where the load is removed from the surface of the crust and the magma can propagate out to the surface, and we get more eruptions. And we actually have quite good evidence of this effect happening from somewhere like Iceland, where the records of volcanic activity are quite good, and also we have a really good handle on the extent of the ice sheet in the past and how that has changed too. And there's a really good relationship between the number of eruptions and the amount of ice on the surface of the planet. So just to give you a context of how important this effect might be, this is a map of the globe with all of the known subaerial or terrestrial, as we call them, terrestrial volcanic systems marked as little triangles here. So some of these might be islands, such as Canary Islands here, the Azores, but others are going to represent the big mountain chains, of course, so in this South America here, or Alaska, North America here. And the red triangles here are volcanic systems which, during the last glacial maximum, so about 21,000 years ago, when the Earth was in its coolest state, were covered in glaciers or ice sheets. So the numbers at the bottom here tell you how many volcanoes there are in each category. So the glaciated ones, the ones covered in ice at that time, are actually more than the ones which were unglaciated. So potentially this mechanism where the climate warming, ice masses melting, and the pressure in the crust changing and the amount of volcanic activity responding, the places on Earth where that can happen are very numerous, and in fact most of the terrestrial volcanoes have been affected by that process potentially. So this is a really interesting example from a bit of research which was published quite recently in 2018 about Antarctica. Now, we don't know a great deal about the Antarctic, the subsurface, or the subglacial parts of Antarctica. This research was effectively undertaking a survey of the land underneath the ice in Antarctica. And the map down here shows you the locations of some of the 91 potential volcanic systems that were discovered underneath Antarctica. Now, that volcanic system might look a little bit like this representation here in this block diagram. So we've got a volcanic system here, which may or may not be active at the moment, with a huge amount of ice from the West Antarctic ice sheet sitting on top of it. Now, of course, we're in this situation now where that ice is beginning to melt in response to human-induced climate change. And so this mechanism of ice melting, releasing pressure on the land underneath, and that encouraging fractures to form in the crust and magma to escape, might well be kicking in or starting to kick in Antarctica. At least it has the potential to do so. And if we think that those volcanic systems themselves have the potential to melt the ice that's on top of them, then we can think that there might be some pretty serious feedback effect going on. So the ice melts due to global warming. There's less pressure on the volcanic systems. That encourages more eruptions, and of course more ice melts as a result of those volcanic eruptions. And we end up with this cyclical feedback system where we could end up with the volcanoes and the climate change between them melting the ice of the West Antarctic ice sheet. So this is certainly new research, but it's certainly interesting and highly concerning in the context of contemporary climate change. Now, of course, when all that ice melts, it has to go somewhere, and the water that results from that ice melt ends up in the seas. So this is a nice representation here of an ice sheet during a glacial period. And as that ice sheet grows, it's taking more water out of the sea, and the sea level is falling. During the interglacial period, when the planet's heated up, that's the situation we're in just now, the ice sheet retreats, it melts, and of course that water ends up in the sea, and we end up with a sea level rise. Now, it's not widely appreciated, I don't think, how large that sea level rise in the past has been. So during the last glacial maximum, about 21,000 years ago, when the Earth was considerably colder than it is now on average, and the ice sheets were at their maximum, sea level was about 100 meters lower than it is at the present day. So just to give you a context, that could be the equivalent of pretty much all of the English Channel being dry. So during that time, you could more or less walk from England to France without getting your feet too wet, with the sea level being 100 meters lower than it is at present. It's a very significant change in sea level. And of course, with that change in sea level comes a change in the mass that's exerted on the surface of the Earth. So, to go back to our volcanic systems, we might expect there to be an influence of sea level change on volcanic activity as well. So, as the ice melts, the sea level rises, what happens to volcanic systems that are in the sea? So a really nice example here is this island of Santorini. This is in the Mediterranean. So here's a map to show you where it is. Here's Greece, Turkey, Crete, and the many Greek and Turkish islands of the Aegean Sea. Santorini is one of those. It's this incredible ring-shaped island, which you can imagine used to have a volcanic peak in the center, which has collapsed in previous eruptions. And the center of this volcanic system is filled with the sea. So if any of the world's volcanoes are going to be affected by sea level change, then probably Santorini is it. It has some new volcanic activity. The last eruption was in the 1950s. That's this little island here in the center of the ring. So this was part of my own research with research collaborators, a team of us, who decided that we would look for evidence, look to see if there was any evidence that the sea level change would have an impact on eruptive activity at this volcanic island. And Santorini is this amazing place. It's a very beautiful place to go to, and it has this incredible record of past eruptions stacked in its cliffs, with the most recent eruptions at the top, and as you go down through the cliffs, the eruptions get older and older and older. But it's a very complete and very well detailed record. So what we wanted to know was, is there any relationship between what the sea level was and the number of eruptions through time? Looking back hundreds of thousands of years of volcanic activity of this volcanic system. So this is what it looks like close up. These layers here are individual eruptions. They're layers of pumice and ash which were deposited up to 360,000 years ago. So this is a diagram which summarizes how the eruptions have changed through time. It's a little hard to get your eye on this, so I'll walk you through it. On the x-axis here, this is the age of the eruptions going back through time. So 0 here, this is the present day. 50 is 50,000 years ago, 100,000 years, 200,000 years, 300,000 years, all the way back, 400,000 years, right at the end here. And these bumpy lines, these look like mountains here. These are representations of the number of eruptions going through time. So the bottom line here is all of the eruptions of Santorini. This line here is just eruptions of lava, so these are relatively minor eruptions. The next line up here is a representation of the number of what we call interplinian eruptions. These are explosive eruptions, but they're not huge eruptions. And finally at the top here, these dots, these circles, represent the very largest eruptions of Santorini. These are cataclysmic eruptions where perhaps a lot of the island is destroyed in the process. These might themselves create tsunamis in the Mediterranean Sea. Okay, there's not so many of those, so only 12 in total. So what we found was that the number of eruptions varies as you go through time. It's not constant. And there are time periods where there are a lot of eruptions, here and here. So around about 20 to 25,000 years ago, and then around 60 to 70,000 years ago here. And then another peak here around 150 to 175,000 years ago. And we noticed also that there are these time periods where there are very few eruptions at all, hardly any. Okay, so the volcanic system is pretty quiet. So the question we were asking was, is this related to sea level change? Is the climate of the Earth altering the sea level and in turn having some control on the eruptions of this volcanic system? So the way we investigated this was to create a model. This is a computer-generated model of the Santorini volcano. So this is the island here. It's the familiar ring shape that we saw in the photograph earlier. And underneath the island system, there is a shallow magma chamber. We know that. And then there's a deeper reservoir of magma. This is a pretty classic setup for a volcanic system. So what we know is that fractures will propagate from this shallow magma chamber up to the surface and allow magma to erupt when the excess pressure in this chamber is great enough to fracture the rock around it. And we know that that can occur by two mechanisms. Either we can fill this magma chamber with enough magma to create that overpressure, or you can reduce the pressure, the overburden pressure as we call it, by reducing the sea level. So that if the sea level drops far enough, that might itself be enough to fracture the rock and get that magma up to the surface. And this was the result of what we found. So this is a sea level curve on the top here, this top panel, this blue line here. So you'll notice that the sea level through time, again this is 400,000 years, 300, 200, 100, the present day, the sea level has changed hugely through time. So we have a drop here to 110 meters below the present day, and then a really rapid rise up to near what it is the present day, and then we have a fall and a rise, a fall and a rise. This repeated pattern of sea level rising and falling over time. The most recent rise is from our last glacial maximum when the Earth was really cold and all that water was locked up in ice, and the sea level there was around 100 meters to 110 meters below the present day. That was around 21,000 years ago. Then the Earth had this period of rapid warming, and the ice filled the ocean basins again and raised the sea level to what it is today. So that's the sea level curve at the top here. And these brown stripes here, these brown boxes, indicate times where our computer model indicated that that sea level drop was sufficient to fracture the crust and get magma to the surface. And you can see that there's a really good relationship between those time periods and the time periods where there are a lot of eruptions happening from Santorini. That's here and here. In fact, the relationship is very strong. So there were 211 eruptions of this volcano over the last 300,000 years, and 208 of them occurred during time periods where the sea level falling by itself was enough to fracture the crust and get magma to the surface. When the sea level rises again, as it has done recently, that's effectively enough to close those fractures up and prevent all but the very largest eruptions happening. So those results have some important implications for the hazard assessment. This is the beautiful island. This is the beautiful town of Thera. This is the capital of the island of Santorini, right on the cliffs of the volcanic system here with the sea below. And here's another image here showing the top of the cathedral. And this island here in the center is where the most recent volcanic activity has taken place. And it's all been very minor. It's lots of small lava eruptions. And as I said, the last eruption here was in the 1950s. Now, the present hazard assessment is that this kind of activity would just continue into the future. And it's unlikely, they think, that the very largest, these Plinian, very explosive, destructive eruptions would happen at all. But because we now know that the sea level is one of the fundamental controls on eruptive activity here, the study that we undertook showed that these minor eruptions that have occurred recently are actually due to stop because the sea level's risen sufficiently now to prevent those fractures from forming in the crust. And in fact, some magma was injected into the base of the system recently in 2011 and 2012, but it didn't make it to the surface, so perhaps that's the effect of the sea level suppressing that volcanic activity. But very, very large eruptions could still occur because by injecting huge volumes of magma into the magma system, you can still fracture the crust that way. So we're going to leave volcanic systems now. We've understood that both ice melting and sea level change resulting from climate change can impact volcanic eruptions and volcanic systems. And we're going to turn our attention now to earthquakes. Now this is an amazing image of the destruction caused by an earthquake in the Alps in Switzerland. This is the city of Basel, depicted in 1356, and this was the time of probably one of Europe's biggest earthquakes on record. So the estimated magnitude for this earthquake was magnitude 7. That makes it a highly destructive earthquake, and actually one that we would not expect from the geology that we understand of the Alps these days. We do get small earthquakes in the Alps, but we wouldn't expect one of a magnitude 7 to occur. The entire city of Basel was devastated by this earthquake, and if this occurrence was to repeat itself, the consequences would be very severe today. The city is home to 500,000 people, and interestingly, and perhaps more problematically, it has a pharmaceutical industry which supplies about 10% of the world's medicines. So you can imagine that a natural disaster in this location would not only have profound implications for the people of Basel, the town itself, but perhaps even for the world's pharmaceutical trade and industry and healthcare. So it's a really interesting case study. Now, I mentioned that the magnitude of this earthquake back in 1356 was far beyond what we would expect normally in the Alps. And the reason for that is thought to be, again, because of the removal of mass from the crust due to deglaciation. So this is a map here which represents the outline, what we know of the outline of the glaciated area of the Alps, extending into Austria, Germany, France, and Italy here, and covering most of Switzerland. at the peak of the last glaciation. So this is again about 21,000 years before the present. Now the ice here could be up to about 2 kilometers thick in places, a very significant mass placed on the surface of the Earth. But as we know, the Earth warmed significantly and very rapidly after 21,000 years, and by about 12 or 11,000 years the climate was looking much more like it is today. But that has obviously resulted in a much reduced ice covered area of the Alps. So this white area here is the maximum extent of ice coverage in the Alps today. So we've removed a huge amount of mass from here, and the thinking is, just as with our volcanic systems, that the removal of that ice has allowed fractures to form in the crust, maybe reactivated old fractures and created earthquakes that way. So we don't have very good evidence in Switzerland in terms of field evidence of this, but if we look at Scandinavia, if we look at Norway, Sweden and Finland, we have much better field evidence there. And this is an area of the world where the removal of the glaciers has resulted in a huge amount of uplift of the land. So this is a map here. Here's Norway on the left-hand side, Sweden in the center, Finland over here. And the colors on the map here represent the amount of uplift that has occurred or is occurring right now in Scandinavia. So right in the center of the Scandinavia, where the Scandinavian ice sheet was, the land at the moment is rising by about 9 or 10 millimeters every year. Now that doesn't sound like much, but cumulatively over about the last 15,000 years, the removal of all that ice has resulted in over 100 meters of uplift of land. So to put this in, if you want to imagine this, imagine where you are sitting right now, and imagine a point 100 meters above your head. It's a very significant distance, and for the land itself to move that far creates a lot of movement, and that movement has to be accommodated by faults. Some of those faults are new. They've resulted directly from the rebound of the land after the mass of the glacier has been removed, or it could be old faults which have been reactivated during that time. So this nice diagram under here gives you that situation. So again, we've got this glacial system, this ice mass sitting on top of the Earth, and underneath that mass, the crust is flexing downwards. It's called crustal subsidence. If you remove that glacier, then the crust rebounds. It's called isostatic rebound, and we can create fractures in that crust to accommodate that movement. And of course, where you get faults, we get earthquakes. Now here's a really nice case study of one of those faults in Norway. This is called the Parvi fault. It's very, very long. It's in both Norway and Sweden here. It extends across this line here. And here's an aerial photograph of it. You can follow the line of the fault here. It's very visible on the landscape. And here's a close-up here. So this is a very long fault. It's 150 kilometers long, and there's a pretty good relationship between the length of a fault and how much it can move. So the longer the fault, the more displacement you can get on it. So this particular fault here has had movement of about 15 meters of movement just in the last 15,000 years. And that's a very significant amount of movement in such a short period of time, relatively. So this is a nice diagram which represents that. Again, here is time on the x-axis. Here's the present day. Here's 10,000 years, 20,000 years, 30,000 years, 40,000 years ago. And this block here, this grey block, represents the size of the ice sheet over time. So the size of the ice sheet was at its peak here around 15,000 years ago, and then dropped off rapidly to the present day. And during that time, this fault, this Parvy fault, has slipped 15 meters. It's a huge displacement just in this very short time frame of maybe 2,000 years, between 8 and 10,000 years ago. Now, if all that slip happened at once, if you had this sudden shift happening all at once, this would have resulted in a magnitude 8 or 9 earthquake. In other words, one of the largest earthquakes ever recorded anywhere on Earth. Now, we don't know if that movement all happened in a one-er or if it happens incrementally over time, but it's certainly possible that the removal of the ice through warming resulted in a very substantial earthquake. Now, earthquakes have a lot of potential to cause additional hazards. One of the most obvious is tsunamis. Now, earthquakes can obviously create tsunamis when they occur under the sea, just by displacing the water, and that in itself will create a tsunami. But they can also occur, they can also create tsunamis when the earthquakes occur on land, and they can do that by creating landslides. So this is a really nice map here which shows deposits from landslides that have occurred in the past. So some of these deposits are absolutely huge. We're going to look at this Storiga landslide in a little bit more detail. This deposit here represents 3,500 kilometers cubed of rock and sediment that slid off the coast of Norway into the North Sea. And just like dropping a brick into a bath, this creates a huge displacement of water and a tsunami. So we're looking here at a situation where Great Britain can potentially be hit by tsunamis. And in fact, there are deposits in Shetland, in the north of Scotland, and in the Faroe Islands, which demonstrate that in the past, around 8,200 years ago, these areas were hit by a tsunami. It's not normal really to think of the UK as being at risk of tsunamis, but here we are, they've occurred in the past. Now, this huge landslide was probably triggered by the post-glacial rebound earthquakes we've just been talking about in Norway and Sweden. This is a further map to show you the magnitude of the wave that would have been generated by this landslide. In the Shetland Islands, a wave perhaps 20 meters high. In the Faroe Islands, maybe 14 meters high, and even here on the east coast of Scotland, 3 to 6 meter high waves would be crashing into the coastline. And of course, these days we've got vast amounts of infrastructure and cities peppering our coastline around Scotland, around the whole of Scotland, but also down the east coast of the UK as a whole, all the way down to London, of course. And here's just an image. This is, of course, not the UK. This is in Japan. This is the 2011 Tohoku tsunami in Japan, just to give you a visual image of the kind of horror that these events can unfold. So, in summary, we've had a look at 3 different types of hazards. These are hazards of the solid Earth. We've had a look at earthquakes, volcanic systems, and tsunamis, and examined the relationship that they might have to climate change. It doesn't seem obvious at all that the climate changing, the climate warming, the climate cooling could influence these hazards, because they're not atmospheric hazards, they're hazards of the solid Earth. But there is a relationship. We know that ice melting can cause fractures to form in the crust and create earthquakes and volcanic eruptions, encourage volcanic eruptions. We know that those earthquakes in turn can create tsunamis. If they occur under the sea, they can create tsunamis by themselves, and if they occur on the land, then they can result in landslides, which can create tsunamis. And we've also seen how sea level rise might influence volcanic islands. We looked at Santorini, the island of Santorini, and noted that the sea level rise might reduce minor activity there, but the risk of very large eruptions may remain. So that brings to an end this school's lecture. I hope it's been informative and enjoyable for you. You can find out more information about the kind of activities and events that Royal Holloway Geography runs at this web address. You can follow us at Royal Holloway Geography. We've got a YouTube channel, Facebook, Twitter, and Instagram. And I want to mention as well that we now have a team of schools ambassadors. These are our amazing students here at Royal Holloway in Geography, who have been trained by the Royal Geographical Society to become schools ambassadors. And if you're interested in booking one of those for a visit, then you can do so through the Royal Geographical Society. Here's the web address here. Or you can contact myself at Royal Holloway as the school's outreach officer, and we can try and arrange a visit for you. So that's the end of the talk. I hope it's been enjoyable, and you can follow up as well with the accompanying activity.